Okay, so you have this system with two blocks, which is two masses, and there are multiple pulleys. And at one end of the pulley, there's a spring that's holding up everything. So everything starts from rest, and A start from rest. And if you release A, you will see it will drag all the ropes, and the rope will drag the B, and will stretch the spring, right? So the initial length of the spring, let's call it L0. That's the initial length of the spring. And at one moment, and the spring is stretched to delta L. Just that's at one moment, one instant, when MA is falling, then the stretch of the spring is delta L. And we're trying to find out what is the VA, speed of A and speed of B, when this stretch of spring equals delta L. So this is a setup of this problem, and we're gonna look at this problem and work through everything together. So because in this section we talk about work energy equation, so I would jump to work energy equation by writing out what are the work energy equations, and that's kind of show you how to start. So work energy equation is T2 plus V2 equals T1 plus V1 plus the work done by the non-conservative forces from position 1 to position 2, right? That's a work energy equation we learned in section 4B. And so there's during the 5 steps, 6 steps approach, I told you, you will need to write out all the kinetic energies for each mass, right, as step 3. So, and there's actually one kind of trick I learned from Dr. Teicher, which is another, it's very good. It's to create a table for your kinetic energy for each mass. So T1, T2, you can list the table like this, and you will have kinetic energy from each mass in your system. So in this example, we have two masses, MA and MB. So you will have kinetic energies from MA and MB in your table. If your system has more than two masses, then you're gonna add more math in your table. But in this case, we only have two. So if you look at the kinetic energy for both MA and MB at position 1, and this problem starts from rest. So it releases everything from rest. Therefore, at position 1, there's no movement at MA and MB. So we don't have any kinetic energy at position 1. And since we're looking at what's the speed of A and B at this moment when the stretch of spring is delta L, so we know we probably have kinetic energies at position 2. We just don't know what's the value. And that tells us we can write this as 1/2 m a v a squared. Same thing for mass B, that is 1/2 m a v b squared. That's B. Oops. Okay, so that's the kinetic energies, which is not too bad. But the next step in your solution is you need to find all the forces, all the work done by the forces in your free body diagram, right? And so the work done from 1 to 2 by all the forces. Then if your force, any force is a conservative force, then you can write that work as the potential energy at endpoints as V1 and V2. V1, V2. Okay, so this is kind of like two different ways to write either potential energy or work. And you can also create a table for this, but in this table, you would need to consider all the forces in your system. And in order to do that, you need to have a free body diagram for the system. So let's look at this system. If I want to draw a free body diagram for this system, so what would I do? So I would start from MA, which was red. Start from MA here and goes up. This is pulley, goes around another pulley, and here has a tension force T at M. Here we have weight force WA. And on the other end of the pulley is connected with another block. It's called, has a weight force WB. And there's another rope wrap around the pulley, goes down, and there's a spring force Fs is pulling this rope down. And at the pulley, remember we have two pulleys here to tighten up the rope. So at there should have reaction force R2 and reaction force R1. And what other forces we should have in our free body diagram? Don't forget this block B is sitting on the surface, therefore there should be normal force MB goes up, right? And also there will be friction force there too. So those are the forces in our free body diagrams. And did you notice I didn't consider the tension force in between the pulley and block B? This is because I take the whole system for my free body diagram. So the tension between this pulley and this block, it's considered as internal forces. So you don't need to add internal forces in your free body diagram. Okay. Now we can starting to fill up our table with the work or potential done by each force. So let's start with R1, which is reaction force. R1, and what's the work done by R1? So if you look at R1, and R1 is the reaction force at that pulley is fixed there. And is there any movement or motion along the direction of R1? No, there's no movement along that direction. So that tells you there's no work done by R1. So the work done by R1 is 0. 0. And same thing for R2. Since the pulley is fixed there, and even there's reaction force, but there's no motion along that direction. So R2 equals 0 as well. And in another word, you can think about this way. Even the rope, it's moving, right? But the motion of the rope, it's perpendicular to that reaction force R1, R2. Therefore, no work being done by the reaction forces. So that's just a different way to look at that problem. And now let's look at another force. Let's look at the normal force of block B first. So the normal force of block B is pointing upwards, but are there any motions on that direction for block B? No, the block B only moves on horizontal direction. Therefore, the work done by N, the normal force of B, equals 0 as well. Let's keep extending this table. Now let's look at another force, which is a tension force here at the end of the rope. What's the work done by the tension force? And the work done by the tension force, to answer that question, to figure out, are there any movement on that direction? So if you go back to the system, this rope, the end of this rope is fixed on the wall, so there's no displacement of that tension force. Therefore, the work done by T equals 0 as well. Okay, now let's move on to the next force. We have a weight force WB here. WB, and it's pointing downwards, no movement, and there's no change of height. Or another way is you can set up a reference potential line. Let's call it this line as the potential energy equals 0. So at that height, the potential energy equals 0 for block B. And since block B only moves on the horizontal direction, so at position 2, there will be no potential energy. It will be the same potential energy, same height, therefore V equals 0 at both V1, V2. As you may notice that, start from this wave force, I write the potential energy instead of work done by the wave force. That's because the wave force is a conservative force. So it can be written as the potential energy V1, V2. Okay, next we have the wave force VA. And let me finish the rest of the table. It says potential VA. What other forces we have on our free body diagram? We have this Fs, which is the force from the spring, as well as the friction force Ff. So you would need to find the work done by the Fs and Ff. Okay, we still have 3 forces left for potential energy or works. I would like to break you guys into small groups and give you some time to work on this and to see if you are able to fill out this table. So let's use a cool functions called break rooms. How do I do that? Let me see if I can find that function. Oh, never mind. I don't think I can do that today for some reason. Oh, I got it. Let's do 2% group. Let's do 4. Okay, so you will be assigned to, oh, that's too big. Like 4-person group, I guess. And then you can work on this together. You're able to talk with each other.
I've figured out how to do the work done by the friction. So this is going to be mu sub k times the normal force of mass B.
What's the direction? What's the sign of the work done by the friction? Should that be positive?
Oh, that's going to be the negative I direction.
Yes, so always remember the work done from the friction force always negative. So always add that negative sign there.
Okay.
Okay, I would like to see the rest of the group and join the discussion to see how to find the work of potential from the rest of the three forces. All right, are you guys doing good?
Yeah, we're all good in here.
Okay, who can tell me what's the work done by the spring? Okay, this is supposed to be a kind of group discussion, so I want to see you guys like discuss how to do this problem with each other.
Would the work done by the spring be that K/2 minus the delta L squared plus L squared equation?
So the work, so first question is, is spring force a conservative force or non-conservative force?
It is conservative.
So if that is a conservative force, it can be written as V1, V2, right?
Right.
So what's the potential energy for spring at position 1? If everything starts from rest, there's no stretch.
So 0.
0, yes. So you will put 0 in the table for V1. And for V2, that's a potential energy for the spring at position 2. So position 2, the spring is stretched at delta L. And the equation for potential energy for spring is K/2 times delta X squared. So that's the correct equation. So in this case, we need to replace the delta X with delta L as a displacement of the spring.
All right, thank you.
Okay, yeah, and then I want you guys to discuss for the rest of the two forces, WA and the FF. Okay, what's going on here? Just one person. Okay.
Yeah.
All right, are you guys doing good?
Dr. L, when you're solving for mass A, would you use the kinetic energy equation and just rearrange it for MA?
No. So for MA, for the what you mentioned, the kinetic energy, we already finished that. The first table we had for T1 and T2, taking care of the kinetic energies.
Okay.
So what are we doing here? forgot all the kinetic energy what we did. Here we want to find out the work or potential energy from
Oh,
force. So if you look at that WA, that's a wave force from A, and
Mhm.
the potential energy of that gonna depends on how much that mass is moved on vertical direction,
Mhm.
right? So first question for you is, it's the weight force a conservative force or non-conservative force?
It's a conservative force.
Yes, so it is a conservative force, therefore it can be written as V1, V2 as
Mhm.
potential energies. So V1, which is a position 1 for that block A, you can set up the zero potential for the initial point or whatever you want, wherever you want. So I would use the initial position 1 as the zero potential kind of datum reference. Then, so V1 would be 0. At V2, if we stretch that spring to delta x, and which means MA will move downwards to a certain distance, right? So
mhm.
Yeah.
at position 2, the potential energy of MA equals negative MAG times H. That H is the distance it moved downwards. And
Mhm.
the tricky part is, what's the H? Is H equals to delta L? So you can think about that. If we only have one rope in this problem, the rope is connected all the way from spring to mass A, then we probably can see the movement of MA H equals delta L. However, if you look at this problem, we cannot have two ropes. So there's a relationship of the how things moves. I want you to think about that. I will mention that, go through that later. So you guys can have a discussion on if what if the displacement on the spring is L delta L, what's the drop of MA would be? Okay. Okay, I'm gonna check on other rooms.
Hey, Dr. L,
Uh-huh.
what is the distance between block A and block B?
Distance between block A and block B. I don't think we need that distance in this example. You don't need that information to solve this problem.
Then I guess I mean, how do you know the potential of A?
Potential of A. So just like I mentioned, A will only move up and down, right? So at the initial point, it's A start from rest and you release A. So A will move downwards, but we don't know what's the distance that A drops. But we know in this problem is the stretch of spring is delta L at one moment. So I think the tricky part in this problem is, if I tell you the stretch of the spring is delta L, are you able to find out what is the kind of the movement of MA? So that requires something we learned from chapter 2, pulley and ropes. Okay, I will tap on that once I close up this breakout room, so we can have the discussion on that.
Okay.
Okay, now we're all back to the main section. So that was the task for the breakout room. That purpose of that is kind of like to put all of you in small groups, and so that you can have like discussions within your group. But somehow I saw some of you are able to talk, but some other groups, I think there would be must be internet connection problems there. Or I didn't see any discussions. But however, let's go back to this problem. So let's first look at WA, the work done by WA. First, this WA is a wave force, which is a conservative force. Therefore, can be written as V1, V2, right? We can first set up by saying that the zero potential datum for the block A is at position 1. And then at position 2, it will drop to a new position. That's called the H. We don't know what H is. Therefore, we can write, at least we know at V1, that is 0. At V2, and that equals to MAG negative, negative H. Let me erase this. So it's negative, right? It's going downwards. So negative MAG H. And we don't know what is A in this problem. However, we know this. We know delta L, which is a stretch of the spring, right? The elongation of the spring. And can we find a relationship between this delta L and the H? Write it down. Delta H. Is delta H equals to H? Or delta L equals to H?
Yes.
If you say yes, and
It wouldn't be.
you were lost the points for this question.
Come on, Dr. L.
So if we only have one rope that connects from the spring to the block M, and I would say yes, delta L H. However, if you look closely, we have one rope here, another rope, another rope. So it's more complicated than that. So hopefully you still remember the pulley and rope problem we did in chapter 2, I guess. That's chapter 2 or chapter 1. And let's do that. So let's write down, just take a look at this part of the pulley. So
Hey, Dr. L.
yes.
What's the purpose of the R's?
R's are the reaction force at the fixed pulley.
Are they important?
They, what we did is they don't do any work to the system. So the work done by them are zeros from R1, R2. It is important for you to recognize those, but since their values are zero, so they're not very important in terms of how to solve in this problem. Okay, let's look at the pulley in this part of this problem. So if you remembered what we did in chapter, I think that's chapter 1 or 2, is we can list the length of the rope, right? The total length of the rope equals to, we can call this part as SB, and we can call this length here, this is a block, SA. And what's the total length of the rope gonna be? It's gonna be SA plus SB here on the top, and also on the bottom here we have another SB. So there will be 2 SB, and you need some other like constant length in the loop. And other constant lengths, what I mean by that is the length wrap around this pulley here, and some lengths around this pulley. We'll consider those are constant lengths of the pulley. Then we can take a derivative of this length on both sides. Then we have L dot equals to L plus 2b plus 0, right? And L dot, since the total length of the rope is constant, so 0 equals SA dot, that would give you VA. As 2SB dot, that would give you VB. So 2VB. Therefore, we can find out the relation between VA and VB. So VA goes to negative 2VB. So this tells us VA is moving 2 times faster than VB, right? VA is moving 2 times faster than VB. So on the VB, it represents how fast this block B is moving. Block B is connected to the spring. So if the spring is moving delta L, then the block B is moving delta L. But MA is moving 2 times faster than this. So the H, how fast, how much this MA drops, H equals 2 times delta L. So that's the correct relationship between L and delta L. And if we know that, we're able to like change this term here to negative MA, replace H with 2L, 2 delta L. So that's the potential energy at position 2 from the wave force. Okay, any question on that? So that's kind of the tricky part. When you have pulleys and ropes, don't just assume the displacement are equal. So you need to do some analyze to make sure the correct relationship between two blocks. Okay, then we can move on to the force from the spring, Fs. And Fs, it's a conservative force. Therefore, the work done by it can be written as V1 and V2. And at position 1, everything is released from rest, so there's no stretch on the spring. So we can see that's 0. But V2 of the spring equals 1 over 2 times K times delta L squared. That's the equation for potential energy. Let's raise this. That is K over 2 delta L squared. That's a potential energy from spring, and it is always positive. Remember that. And next, we only left this friction force. And what's a work force? And if you remember, the equation is you take the derivative, the integration of friction force on the ET direction ds. That would
How are you, Mommy? Good, how are you?
Work done by the friction force. And since in this case, the friction is pointing downwards, it's constant force, and not constant, it's pointing to the right, it's a constant force. Therefore, it can be written as negative mu k mbg, right? So mbg will give you the normal force of mb, and mu k, it's the friction coefficient. And pay extra attention to that negative sign there. The work done by the friction force is always negative. So always make sure you have that negative sign for the work done from the friction.
Dr. L,
Yes?
would it be different if the friction force was to the left?
No, doesn't matter the direction of the friction force, and the work done by the friction force will be always negative.
Okay.
And same thing for the spring force. Doesn't matter where's the direction of the spring force, and the work done by the spring force is always positive.
Okay.
Dr. L, for the friction force, the work done by that, wouldn't we have to multiply it by distance?
Oh yes, good catch. Yes, so it's equals Fs, right? The FF is the friction force and S is the path of the how much that friction is doing work over a path. So the S in this case is how much your block B is moved on the horizontal direction. And in this problem, we know the stretch of the spring is delta L, which means the block B is moved the same length, which is delta L. So the S here is delta L. Make sure you add that times delta L. And that is the total work done by the friction force. Thanks for the correction. All right. Okay. Now you should have all the components in for your work energy equation, right? So if we go back to here, the first table, T1, T2, will tell you all the kinetic energy inside of your work energy equation. That's T1 and T2. The second table we created will give you all the potentials and the work done in the system, which will give you V2, V1, and this U, the work done by the non-conservative force. In this case, would be the friction force. And a few more things is, I think the tricky part is this rope relation. You need to able to do the analysis on the total length of the rope to find out the relationship between speed at two ends of the pulley system. That it's kind of the key to solve this problem. All right. Wow, we spent a lot of time on this example, but that hopefully that will be this will be a good wrap up for section 4B. And start this Wednesday, we're gonna look at section 4C. So I can start right down. Get you started on section 4C. So section 4C, it's a little bit different. So in 4B, what we did is we did some modification on this formula F equals ma, and we transfer that into the work energy equation, right? So integration of forces on ET direction ds equals integration mv dv. Then we get the work energy equation as u122 equals t2 minus t1. Then we'll further simplify this to get the work energy equation T2 V2 equals T1 V1 plus U122 non-conservative. Okay, that's what we did in 4B. And in 4C, we're gonna do a different modification on the same formula F equals ma. So in 4C, we're gonna write the acceleration as the derivative of dv over dt. So that's kind of the definition of acceleration, right? It's first derivative of velocity with respect to time. Then we're gonna just throw this dt term into the other set of equation and take the integration. And we end up with, yes?
What is right by the U? Does that mean normal component or
Okay, you mean here U? So this is the work done from position 1 to position 2 from all the non-conservative force. So this is NC, represents non-conservative force, which is friction force in this class. Okay, now let's get back here. So now this sum of the forces in the equation dt equals integration of m dv. Now we have this new modification on the, and then in section 4c, we call this term, the left hand of the equation, as linear impulse. And we call the other side of equation change in linear momentum. So this is change in linear momentum. And so that we're introduced to the new section, which is linear momentum, linear impulse. I'm going to use a totally new method to solve the problems. And this whole thing can be further simplified if we only care about the average force instead of the sum of all the forces. If we only care about the average force, then we can write that as a average times a certain period of time delta t equals m times v2 minus v1. So this is the linear momentum, linear impulse equation. And if we compare this with what we learned in 4b, is in 4b, the work energy equation here, it's a scalar equation. But in 4c, we're gonna go back to the vector equation again. Okay, so make sure you notice the difference. One is scalar equation, one is vector equation. Vector equation means everything should have direction, both direction and magnitude. All right, so that's just a brief introduction to our new section 4C. And that's everything I have today. And don't forget, you will have a quiz due by midnight today. And feel free to email me anytime if you have any questions. And we can set up a Zoom meeting. Okay. Feel free to stick around for a few minutes if you have more questions. Otherwise, you can just hop off.
Dr. L,
Yes?
did you say that you were going to restart that quiz?
No, I mean,
No.
to remind you, we have a quiz.
Oh, okay. All right. Thank you.
Okay.
Dr. L,
Yes?
I was having trouble last time with the audio.
Okay.
So during the lecture,
Mm-hmm.